So thank you very much. So I like sort of casual small meeting, okay? So I don't mind, maybe 1 or 2 audiences enough for me, okay? So, and besides it's a Saturday, I think. Yes, Saturday. So Saturday, at least in Japan, it's a holiday, okay? So maybe here also, maybe, not holiday. So, and nice afternoon, okay? So maybe only motivated person is here, okay? So that's good news for me. So, but I have, how long can I use? Until?
So 1.5.
1.5. So in that case, I can try to entertain you. Entertain means doing demonstration, and at least you can understand what this language is, and in which way we can do some kind of specification development and verifications, okay? So sometimes I need to sit because I want to demonstrate, but so my talk is verifying specifications with proof scores in CafeOBJ. And so CafeOBJ is a language. It is, maybe if you may know, it's classified into algebraic specification language. But from design and inherently, this language is executable. So it can be program language. So I and my colleague is teaching functional programming using this for the master student, you know. So supposed to be maybe the first language for doing programming, okay? And I think it's quite efficient to teach such kind of very, you know, foundational stuff or introductory. But at the same time, this is not programming language. This language is not supposed to develop systems which do some service, real service in real world. It's a specification language and executable. Means the purpose of this language is writing models, okay? Writing models of your problem, any kind of problem, or writing model of your algorithms or systems, any kind. And by execution means it's an inference. It's very honest to the logical inference. It's equational logic inference. So that means you can identify or you can check what kind of property the specification you wrote have, you know. So it's very important before making some, you know, coding or any kind of development. So that is the main role of specification language, formal specification language. I'll explain it a bit. So my talk is about this, but proof score is a main topic, and proof score is some code written in this language which is supposed to prove something about the specification. Okay. Okay, that is overview. So verifying specification, how to develop specification, how to verify, you know, specification using these techniques, this language. Okay, before that, I think it's better. I usually explain, starting my talk about explaining my name. Of course, you two already know, so, but okay. This is my first name. No, sorry, this is my family name, okay? So the last name, family name. This is my given name. In Japan, always only 2, you know, name is composed by family name and given name. Some of you have a middle name, or in some countries there are many components in names, but in Japan only 2, you know. And this is my family name written in Chinese character, but it's used in Japan. Of course, as you know, Japan and China share the cultures, okay? Because the Japanese cultures come from the continent through the China and Korea. It's a historical fact, so nobody can deny. So this is a Chinese character. So Chinese people, maybe we don't have a Chinese student today, but Chinese can read this, okay? And read this. So this is a Chinese character, 2 Chinese characters for my given name. This character means 2, okay? This character means tree, the tree, you know. So my name is a double tree or binary tree, okay? 2 trees. And this character means a thick book or something. It's a plenty of something, okay? And this character means lucky, okay? So, of course, you know, every parents want to give a good name to their children. So that's my name, okay? And this institute, to Alexander, Sasha already knows that because they visit the Kanazawa, beautiful town, also visit this school, I think. And this is a new idea. It's fully supported by Japanese government, really fully, All money comes from the government. So it's a national university. But it's only 20 years. It's start operation in 1992, okay, 1992. So it's exactly 20 years. 20 years of university is very little history, okay? It's very young university. And this university only has a graduate school, no undergraduate student, okay? No undergraduate. And so it's a sort of university at the same time research institute, advanced research, advanced education organization doing the advanced research also. So I am now a professor of this school at the same time director of this research institute, okay? So this is really also new one. It's just 2 years old, And everything I am going to talk is here, my web page. So just write down this, this URL is, if you're interested in. Of course, if the organizer wants, I'm happy to leave my PDF file, but you can download from PDF file here. And all CafeOBJ code I am using today is here, okay? So if you are serious, please just write down this. Other thing is getting from this, okay? So this is JIST homepage, and this is my given name and talk. And Computer Science Club, St. Petersburg today, okay? Yeah? Oh, I see. Okay, so that's fine. So that is a sort of premium. So I'm going to talk about, maybe you attended my previous talk. I am giving 2 talks in St. Petersburg. This is my first visit in this town, and I gave another seminar the day before yesterday. So this part is the same, but I hope you don't mind somebody, And this is a very overview of a formal method and something. And the introduction to this language by using, I am going to do the, demonstrations, writing machines, and just step by step explain this. And plusquare, what is a plusquare and tone? This is usually we gave the lectures in the JIST about this, and it's usually 2 kinds. Elementary one, 14 times 90 minutes, and so on, so on. So at least this kind of thing is 19 minutes times 2 or 3. Okay, so it's. But today I'm using really simple, the simplest kind of example. So I hope you can understand. If you will at least don't sleep and wake, listen to the 30 minutes, I think you can sure understand. You surely understand this, okay? And the other part is a sort of background and so on, so on. So I'm going to start about my standpoint, or maybe our group's strategy to do these kind of, researches. And after that, I'm going to introduce you very simple example. By using simple examples, introduce CafeOBJ language and specification development and plusquares. It's some kind of puzzle, okay? So if you are, maybe almost you are interested in using computers or programming or some kind of hacking, strange kind of language, somebody I hope, like this kind of things. Okay, so our perception. So formal method is now talked by many people, at least software engineering related, software technology related, and this is considered to be not everything, but one of the most important technology to make software development more reliable and more, the modern, efficient. But there are, of course, there are many opinions and there are many standpoints. There are many research groups around this formal method. Of course, formal method is, first definition is using proper mathematics to system development, okay? software development. So there are many, but in this case, discrete mathematics, set theory, algebra, and so on, so on. So this is my sort of dichotomy of this methodology, okay? So formal method can be applied post-coding, that is, if you develop or if already developed the code, C code, Java code, any kind. That code can be analyzed mathematically or using formal method and improve, for example, static analysis, okay, and some kind of verification. You can call it sort of reverse engineering. Reverse means you already have some huge code and want to analyze such code. That is really important, okay? And quite a few companies earn the money doing this, and it's quite important activity. For example, as you know, maybe Microsoft spend really big money to do, so improve their code. For example, this is not Microsoft, I think Apple is also doing some similar things. Okay, the other one is pre-coding. Pre-coding means before doing the coding, you need to do something. System specification, design, or model analysis, and so on, so on. Or even without coding, without developing any kind of programming, this kind of technology is better to be used to analyze the problem you want to, implement in the software and so on. So pre-coding and post-coding. And of course, this is, we call it other ways upstream, more human being side, more design phase, more requirement, more domain side. So, and I think, any sort of, well understood or maybe the established software engineer understand solving this area is really important. And if you can solve some problem in this area, the result is really important. Result is much more, the large scale than here. So successful application of formal method to the area of model specification of domains or requirement, design, architecture can bring drastic good efforts. Maybe it's not quantity, it's a quality, System development is really developed by quality, but it is not well exploited or practiced, okay? So that is our standpoint. So we want to apply formal method to the upstream. That is a simple way to say. And of course, in this case, the formal method is a sort of acronyms. Very large part of the formal method is verification. And so current status is, as you know, model checking is really big success. It's recently maybe at least one or two researchers who developed this technology got Turing Award, okay, successfully. So that implies that this community appreciates their achievement quite a lot, Ed Clark and Pugnelli, maybe two already got the Turing Award. Of course, this is a big success, but at the same time, it has some limitations. Okay, for example, these techniques require you to model the system finite state, and or you are supposed to find nice abstractions. Okay, without such kind of abstraction, it's rather difficult to prove or model check that. And the other way is like some guy who is doing the work in this. I understand this is an Institute for Mathematics, okay? So mathematical proof, some kind of mathematical reasoning is used. So in this case, human being is in charge of analysis. So it doesn't mind, finite state or infinite. But anyway, there is a sort of strong tradition in computer science of software technology to develop interactive verification systems like Isabelle Hall or Koch, PBS. It's the three most famous, interactive theorem provers. Theorem prover is, in other words, interactive verification system. But this is originally designed to do the mathematics on computers. For example, Coq is designed and now actively developed in French people. So France is a sort of famous. They think that mathematics is important to their cultures, to my understanding. It's true still, you know. So that's why French government is happy to support these kind of things. Quite foundational, but it's world famous, okay? And they are serious about making it as a world best stuff. Of course, it's competitive. This one is American. This one is England and German, okay? This is French, this is American. So, but this is, as I said, mechanizing mathematics. So it's not originally designed for the software requirement, okay? So that's why we want to, of course, there are other activities, event B, this kind of interactive verification system is now start to be used in software field. But it's still research stage. So we want to, this long agent system is, of course, not comparable to this, you know. This is really, it's a big project, okay. Many people and many budget is already used. It's not comparable, but we are trying to do the same things in the different approach, okay. So this is a very generic domain requirement design. It's difficult. What I want to say is it's not simple because, you know, it's some kind of doing the new theories, developing new theories. Because if you want to solve new problem in the real problem in some system or develop some computer system, software system which solve the real problem, if you want to be serious and formal method, of course, it's you know, depends on the situations, but to some extent, you are supposed to make models of that problem. Without making model, without writing some formal text, it's not easy to analyze that, okay? So in some sense, you are inherently required to do the mathematical modeling. And recently, prestigious, and of course, I know several software engineering very capable researchers, but majority of them is now start to talk what is the best way to train the capable, you know, super software engineers. What's the best education for the super software engineers? Super means really, you know, not low level of coding, but also design, architecture design, and requirement capture, and so on and so on. And I think it's sort of consensus. I also agree to that is, you know, the best way to train such kind of engineer is to teach abstraction, to teach the ability of abstraction. Or in other words, without the ability of abstraction, software engineer cannot be super engineers, okay? So its abstraction is really important. Abstraction means if you see some real problem, you can identify the basic structure, you know, important structure of that problem and write down some specifications, not code, okay? High level document, which can be understood by the developers, which can be understood by the, you know, some kind of executive who want to spend money to solve that problem, okay? So that is really very important ability for the super software engineers. Also, in some sense, what's the best way to teach such kind of things? I think it's, of course, computer science, foundational computer science should be taught, or maybe mathematical thinking. Anyway, this area is difficult, but challenging, as I said, and it's a really important area. So interactive development of the program is really important. So I think, you know, one way is using this kind of formal method. To teach the formal method is really important. And our approach is, you know, we are not necessarily believer of full automations. Of course, if you want computers, it's better to make fully automated, okay? You want to just push a button and wait and getting a coffee and wait 2 hours or 1 hour and see the result. That is a general tendency. If you want to solve some problem by computers, automation is, of course, ultimate goal considered to be. But in this kind of domains, requirement of modeling in the initial stage of the system development. Full automation cannot be done at the same time. Full automation is sometimes dangerous, because the point is human beings should understand the real issues, okay? So in that case, this kind of technology can help human to understand the reality. So maybe human being and machine capability is nicely blended. So intuition and rigor is nicely blended. And high-level planning and tedious formal calculation is nicely blended. Without collaboration, without nice coordination of such kind of ability, it's really difficult. Full automation is just, in some problem, just impossible. Or if you do some kind of full automatic one, this is a very limited area. Or maybe if you believe any kind can be done like that, that is just mistake, I think, Because, of course, human beings should be responsible of system development, okay? Of course, it's a little bit deep questions, Finally, maybe some robot or maybe some other machinery can decide what kind of system should be developed and maintained. But as you know well, our current society is already heavily depend on the software and computer systems. Okay, so that implies if you that kind of decision is you almost abandon your sort of identities. Anyway, technically I think it's reasonable, this kind of interaction. And Plus Core is of course I will explain in maybe 15-10 minutes the real small examples, but before that a little bit the overview. I can say this is a complete set of symbolic test cases, okay? So verification is a sort of, I think almost all of you is a sort of professional or knows something about the program or softwares, okay? So testing. So of course testing is quite costly, If you are serious about producing software, the final stage is testing. And the company who are producing or making software spend maybe I've heard it depends, but almost half budget is spent to the testing or maintenance. Okay. So maybe if you are familiar with that kind of area, this is easy to be understood. Ordinary software engineers. Verification is a sort of testing, but test cannot cover all cases because test is test. Test is just instance. If you want to test, some function which computes some natural number, okay, testing is just picking up 0, 10, 100, 1,000, or maybe some randomly. It's a just instance, okay? But symbolic test can cover all natural number, If the natural number is less than 10, or if the natural number is more than 10, if you divide two cases, and this case you can test symbolically, this case you can test symbolically, and that case covers all possibilities. That is completely different from testing, so it's rather dangerous to call it test, but symbolic test can cover infinite cases, okay? So verification is easily understand complete set of symbolic tests, because you can do symbolically. Because of that, you can cover all natural number. For example, typical one is in inductions, okay? Natural number can be covered by inductions, okay? If you want to prove some property is hold for 0, and if you assume such property hold any symbolic n, and if you can prove n plus 1, that implies that property should hold 0 to infinity, okay? Of course, it's quite elementary, but very established induction method. Okay, you can think that is a symbolic testing. Okay, you can prove 0 and assuming symbolically n and n plus 1. So that covers everything. So that kind of thing is I call it symbolic. I'll show you the real, more concrete example. You're doing the inductions to do something. So this technique is to prepare the complete set of symbolic test cases by writing down test cases by this language. After developing specification, writing the test case or symbolic test execution using the same language. Okay. So this is considered to be the proof by construction or proof by, we use just a computation or reduction or rewriting. Okay. This is the functional stuff. I'll explain it later. And maybe if you know a little bit about the recent trend in software development, test-driven something is really fashionable, you know, test-driven. So if you make some designs, it's better to design the test cases first, and test case drive the designs and the specifications and the modeling. Very similar. Okay, so from now, very concrete example. So this is a sort of, you know, the methodology, and I'll explain very briefly and try to get into the natural number, okay? It's one of the most the simplest, but at the same time, the most important one, okay? So this is, I gave this talk to the Bertrand Meyer, who is, Professor Bertrand Meyer, who is famous as a designer of the Eiffel language, you know. The day before yesterday, I gave, of course, not a different talk, but this slide is the same. As you know, he is an expert in object-oriented modeling, okay? One of the originators of the object-oriented development, okay? And so this is very similar to the object-oriented development. So I was a little bit, you know, it was a shame to give this kind of talk before him, but he said something. I agree with him, but it's very similar to the object-oriented modeling. But in this case, we call it algebraic specification, and this is called signature designs, okay? And this is a operation, you know. This is a semantic. It's a equation writing, equation development, and then proof scores. I'll explain that. So I don't know to what extent this kind of abstract talk can convey something to you, but I hope you can understand something, okay? If you want to write down some specification or design document or requirement document, any kind, okay? For example, or in other words, if you want to explain your problem to other people, maybe your colleague or maybe your children, or so in this methodology, if you want to use this kind of techniques, the first thing we should do is identify the object, identify the several kind of object. Of course, that is maybe in many methodology, this is the first starting point. If you want to explain your problem, what kind of systematic stuff that is supposed to be by implemented by computers, it's some kind of design. You are supposed to identify. For example, if you want to do something about natural number or stacks or maybe tables or maybe any kind of list of personnel and so on, you are supposed to identify some class of object, several class, several kind of object. That is, we call it sort, several sort of object, entity or data, agent or system, any kind, okay? So this is an important point. Professor Bertrand Meyer's comment is, you know, until this point, it's a big work, okay? To identify the object, it's some kind of object-oriented designs, okay? And this is a class diagram, okay? Class diagram. And after that, in this technology, you are supposed to design or identify the operations or function between class of object. It's quite mathematics. It's algebra, mathematical, okay? Identify the several sort of the object, and after that, identify the function. You want to model some function, you want to model some event, okay? You want to do some dynamism between that. So such kind of things should be modeled by the operations. That's all. And this is a sort of algebraic structures. We call it signature. And after that, you can write down equations over this kind of things. And this is a specification. And plusquise write down after that to verify something. Okay, so it's until now it's quite abstracted. Okay, from now on it's quite concrete. So maybe you can just look into or listen to my talk coming 10 minutes or something. It's really simple things, puzzle. Okay, so it's a natural number. So how to model, or in other words, how to explain your children or your colleague what is a natural number. Of course, for the mathematicians, it's a trivial, but maybe it's not trivial. Okay, I will explain. So what is of course, there are several ways. In these methodologies, natural number is something like this. Okay, 0, 1, 2. Okay, but of course, this implies something, and this is another way. Okay. In this way, natural number can be defined or explained. So, of course, this is already established mathematical tradition. We call it piano-like natural number definitions. So this is exactly such kind of modeling. We can identify, of course, in this case, only one kind of object. It's a natural number. We can call it NAT. We name it NAT, NAT, okay? And there are two operations. 0 is a starting point. It's without no argument, this returns a natural number. This is operators. This is a 0, okay? And the other operation is a successor. This can give you the next natural number. Okay, so that's all. This is, of course, it's a very fancy, clever ideas, but of course, it's not old. It's not Greece age, okay? It's just, I think it's the beginning of 19th century or something, piano in Italy, okay? So it's a rather new idea. That's why this kind of technique is sometimes criticized, too sophisticated or esoteric. But I think I can say this is a sort of established way to explain what is a natural number in computer science or mathematics, I think. Oh, so this is a natural number. So in this language, in CafeOBJ, this natural number is write down something like this. Okay, natural number, this is the name of the sort. We are going to define this class of object. And there are two operations or functions. 0 is a natural number without argument. It's a constant, okay? And the successor, if you give natural number, this guy give you the next natural number intuitively. So this is some kind of this. 0 is a natural number, successor is something like this. And this is exactly this, okay? So this is a definition of natural number. And this is a jargon. Constructor means, this annotation is, these two operation, these two function is a constructing natural number. That's all. So this is this three, this is a comment, okay? This 3 line is exactly definition of natural number in this language, okay? So this is a repetition. I already explained. Describes a programming expression. This is it's just the end of the 19th century, almost 20th century, okay? Giuseppe Peano. Of course, he is a famous mathematician, okay? And it's a sort of established way. It's a very foundational, but I can say this is one of the most important example, maybe the most important example of this kind. Okay, natural number is defined. And if you are software engineers or computer scientists, I think it's a really must of. This is really very foundational in knowledge about. Okay, so I hope you can understand. So this is exactly similarly. Every model, every kind of system description, every kind of specification will be done similar to this. Okay? Simple-minded, but it's working, okay? So that's the point. This system is exactly, CafeOBJ is exactly based on these ideas, in some sense. So natural number is something like this. So the motto, one of the principles is describe a problem in expressions. This is an expression, okay? This is an expression, or mathematical terms or something. But describe your problem by defining this kind of expression or terms. That is a first principle. Any kind of formal method is something like this. Or if you are familiar with any kind of program language is similar to this. Not so exact like this. It's more flexible, more some kind of intuitive. But anyway, if you want to use some kind of mechanical language or program language, artificial language, you are supposed to describe your problem in expressions, mathematically defined sequence of character. No way, you cannot escape from this, okay? But this language is rather serious than ordinary program language, okay? More mathematically solid and rigid. That's one difference, but very similar, okay? Okay, so what can be done? So important point is, as I already said, once you define natural number, something like this, induction can be possible. This makes, the very nice way or mechanical way to generate all cases, okay? As I said, because the point of proof is try to recover all cases. And this is an induction, one induction. So this is a goal, prove that for any natural number n, a predicate, this is a, function returns a Boolean value, okay? Just Boolean value. If you want to prove some predicate hold for all natural number, so this scheme can be used, induction scheme. As I already explained, this is one mathematical notation. First, prove P0, P hold for 0, and assume picking up any arbitrary n, this is a point, symbolically n, and assume Pn hold and deduce successor of n with respect to successor of n P hold. Only two things needed to be verified or checked. This is the first test, this is the second test. If these two things can be done, that property is proved to hold for all natural number. Okay. This induction is just possible by defining natural number by this, okay? The secret of induction is defining natural number something like this. Because of this definition, natural number can be expressed by this. Because of this, induction can be possible. This is quite intuitive, If natural number is something like this, if you some property hold for 0, and if you assume something here, and one step is always can be increased, it's trivial, that property hold all natural number. We have some kind of, picking up somewhere, you can do next, okay?
Question.
Yes?
How do we express that the successor operation gives the next natural number?
Yeah, not because, this is a symbolic representation of natural number.
I mean,
this one?
will a system where the successor operation just gives null be described by the same terms?
Yes. So maybe I don't know whether I can reply to you properly, but the very basic principle of this methodology and idea is modeling the natural number something like this. Okay, natural number is in your brains. Okay, every human being's brain. These are conceptual things. So, in which way you can express natural number, or in which way you can define natural number. So this methodology is assume natural number is symbolically defined by like this.
So I need to assume some semantics for the successor operation.
Yes. Okay. Not semantics. Successor operation is just, this kind of operation. Successor, if you apply the successor, another S is applied again, one more to this. This is expression, okay? So I'm saying, in this methodology, you should understand natural number something like this. 0, S0, SS0. This is a natural number.
Yes.
Okay. And once you agree that this kind of symbolic representative natural number, successor is always giving the next natural number. it's just symbolically applying S again. Okay. So term is, natural number is understood as a set of terms, set of expressions. Once you agree that S is something like this, very symbolic, mechanical function. So if you agree that this induction scheme is just possible. The point is, natural number is a conceptual thing, but you and I should agree natural number is represented by these symbolic expressions. If we agreed, this kind of mechanism is working between us or between many peoples. In some sense, that is this kind, because if you use this kind of, the program language running in some computers, finally it should be symbolic stuff. Okay. Of course, finally it's a bit, but before that, symbol. Okay. Anyway, yeah. Any question you can raise? Okay. This is a sort of computer science like notation. Natural number is a set of expressions, set of terms, symbolic things is defined to be 0 and successor n. Okay. But if you define plus something like this, plus is another operation. It's not constructor, but another operation. Two natural number and can give one natural number. Okay. In that case, this kind of expression is also natural number, n1 plus n2, okay? But we need to define, these two equations. Plus is defined only, these two equations define the plus operations. Because, the first argument is 0 or not 0. 0 or successor, first argument. But natural number is 0 or not 0, only two possibilities. So these two equations is a complete definition of the plus. And if you use these two equations, okay, all of this kind of plus containing expression, of course infinite expression, can be simplified into the expression of this kind. It's a sort of symbolic puzzle, but there is some theory behind such kind of things, So this is very simple, but explains some kind of very basic principle of this kind of methodologies, okay? So other defined symbol, other defined function, this is exactly defined. Plus is defined only two equations. It's quite easy to prove these two equations is complete definition for the plus. Complete means any expression which contains a plus operator can be reduced, can be proved to be equal to the expression which does not contain plus. You can do inductions, okay? Yeah, mathematically, more meta-level induction can be used, okay? Until n plus reduced to nothing, okay? Assuming that n plus 1 plus, symbol can be reduced. So it's quite easy. I think it's very belong to the foundational, of course, not easy, but a very foundational part of the computer science. So in this language, as I said, if you can give this kind of expression to the system is applying this equation from left to right rewriting rule, left to right reduction rule, and reduce this expression to this expression. This is correspond to 2 plus 1 is 3. Okay. So by these kind of things, you can construct any kind of arithmetics over the natural number by defining your function by equations. Okay. So this is a foundation. So what can be done using this? Okay. So this system is quite simple. Okay. Just defining this kind of things. It's a natural number. Okay. Peanut is a Peano style natural number, and plus is declared here, and plus is defined by two equation, and this two equation is used to give you some answer. Okay. So this is exactly, maybe I can show you later, but this kind of things. So the system is doing really simple things, but very powerful. Okay. So the point of reduction, we call it reduction. This is a reduction because this is reduced to this, okay, by using the terms. So reduction of CafeOBJ is honest to the equational reasoning. Means, I don't get into the what is the equational logic or equational reasoning, but it's a very simple, beautiful definition of what is equational reasoning, okay? And I should say in any countries, in Russia, Japan, States, maybe the first mathematics you are supposed to study is how to manipulate equations, okay? I think I'm quite sure, okay? And everybody knows what is the equation, what is the equational reasoning. But I should say it's a really beautiful mathematical achievement. It's already what is the equational reasoning. I can explain in maybe 20, 30 minutes, but it's not topic of this lecture, okay? So if you are interested in, just Google or just Wikipedia, equational logic, you can find. So the point is this language is working honestly. Honestly means consistent to the equational logic. So what this language processor is doing exactly equational reasoning. So it's a logic, okay? It's not computation, but it's a logic. But at the same time, it's a computations. It's a function can be calculated, or maybe expression can be reduced. So this is very important. So this is just a simple language processor. But the most important and the most significant difference of this language with respect to maybe from the Java, C, Fortran, any kind, that kind of program language is not honest to any kind of logic, okay? That is a computation. It's just defined, just designed to be program language, to do the just computations. Computation is sometimes very difficult to be honest to some nice logic. As I said, the equational logic is, I think it's one of the most popular and most important, and maybe every engineer. It's a sort of, I think, established, consensus. Engineer or maybe technology is heavily supported, or in other words, researchers or professors or maybe engineers in any kind of engineer, mechanical, chemical, electrical, or computer science uses the equation. Okay. So equation is quite amenable to any kind of technology and engineers. Of course, very foundational to the mathematics, but mathematics is more fancy. Not only equations, more the variety of logics. Anyway, the point is, this language is honest, consistent. The only thing this language can show you is explained by the equational logic. That's the point. So reduction is just give you some result which can be deduced by the equational logic. Okay. But reverse is not, hold. If you can deduce some result by equational reasoning, that cannot be all given by this language. It's a partial, okay? If this language can give you some answer, that is honest to the equational logic. You can believe in that. But this language system cannot do everything which can be done in equational logic. Equational logic is infinite, interactive stuff. So that is okay, so this is a little bit the same way, If this language shows T1 and T2 is equal, this is really equal by equational reasoning. But if two term is equal, two thing is equal by equational reasoning, it does not imply this can be done by this language, okay? It's a sort of common things, okay? Any kind of proof system, any kind of interact system has this kind of property, this kind of limitations. I can say this, there is no way to escape from this kind of limitations, okay? If you can solve these kind of things, you can solve gathering importance theorem and so on, It's related to the really very deep part of what is mechanically can be done. Okay, Turing machine cannot solve the holding problem, and so on, so on. It's a very foundational part of our business, you know. Mechanical computation, mechanical, you know, the procedure has a limitation. Okay, but it's okay. It's almost established stuff. But even this kind of limitation, computer is really powerful. Okay, you can see almost any problem can be solved. But this limitation should be understood clearly. Okay. Okay. So what can be done? So this is, I think it's interesting. You know. So we already defined the natural number. Okay. We already defined the plus over the natural number. You agree, okay? It's complete. So to prove, this can be proved. This is a very, you know, foundational, interesting property. The plus is associative. Plus is associative means if three natural numbers can be added by first, n1, n2 is done by first, or this part is n2, n3 can be done first. Okay. This equality holds for any combination of three natural numbers. It's an infinite statement. Be careful, it's an infinite statement, okay? So how do you can prove this? Of course, it can be proved. So, but prove means, you know, of course, all thing you should do is only these two equations, okay? Because plus is defined by these two equations. This is the only ingredient. This is only actions, okay, to prove this. So this can be proved, okay. So peanut is first. Peanuts plus is, you know, pair no natural number plus. This is a jargon, just using some kind of functionality. This is a meta module, okay. Anyway, so induction base is we decide to prove this statement, this assertion, with respect to the induction of the natural number, you know, n1. Induction with respect to the first argument, okay? It's okay. So it's a sort of mathematics. So first argument is chosen to do the inductions. So first, 0, okay? Put n1, 0, okay? n1, this, if this can be proved, reduction is just, you know, using the two equations by the right rule, and deduce this part, deduce this part, okay? If this can be proved, the induction base is done, okay? And assuming this, because we are now using induction, doing induction with respect to the first argument. Pick up n1 is symbolically chosen any natural number, okay? Assuming n1, with respect to n1, this equation holds. This is an induction hypothesis. Assuming this equation and won't try to prove this one. Instead of n1, successor n1 is put. Okay.
So the system at this point tries to reduce and prove.
Yeah, I will show you. Deduce this, but and this.
I mean, this could fail if I write something that is not true.
Yeah, if you cannot prove this true, you failed. Okay.
The system will show you that.
Yes. The system show you what is this, okay? So system show you what is this. Only you are doing is two reductions, okay? This second reduction is assuming these equations, okay? I will show you later, very shortly. So if you can see these two reduction returns true, we win, okay? Game is over. This is proved, okay? This is proved means only using the definition of plus, and thus using this kind of inductive argument. Okay, I'll show you, okay? So, I think this is the first example. Okay, this is yes, exactly. Equational. Of course, CafeOBJ is a little bit more than equational logic. it contains several logics. But my talk today and our group's recent activities stick to the equational logic. Okay. CafeOBJ is equational logic plus behavior and rewriting logic. But all proof score is better to be understood as equational logic because it's more, more transparent and easy to understand, and it's sufficiently powerful. Okay. So this is okay. This is a natural number definition. Okay. This is a plus definition. You agree? You already studied this. And this is it's very simple, okay? So just loading this, and this is the Emacs and invoking show and CafeOBJ, okay? And the CafeOBJ is up. So of course there are several ways, but in reading file or maybe just interactively put in. So I will show you in this case. In the listeners, okay, this 2 module is put in, okay? 2 module is put in. So system says, bool is of course default. It's maybe peanut is defined, okay? Defining module peanut. And so we have peanuts plus already. So open peanut plus, and just do this. So this is open means opening the module we defined, okay? Opening module and do just this reduction. This means using 2 equations, okay? Plus defining plus 2 equation, just doing this reduction, this reduction. Of course you can do by yourself, pencil and papers, but this returns true, okay? So it's a sort of trivial, but what I want to explain is what the system is doing, okay? And next step is, so it's not trivial, okay? This is a sort of coding technique. So of course, N1 is declared to be natural number, but N1 is a symbol, just symbol. Any natural number is denoted by N1, okay? It's not specifying the success of something, just N1. So this means this is any natural number, okay? For any natural number, this equation holds. That is intention, okay? Just do this, okay? So this can be, so this equation, of course you can see the equation of something like this. Equation is already put in. So this equation is already in the system, okay? For example, maybe if you show all it's a little bit too much because there is some kind of, the built-ins, but so it's not easy, but show, so this is, so peanut is, of course, maybe this is the only way. This is already, system already know this. Plus, peanut plus is, two equation which defines plus, okay, is used. And reducing this. Okay, and it's true, of course true. But of course, what happens? So if, okay, so maybe it's interesting for you because I think I have a time. So just doing this, okay, this is induction base is rather easy to prove, okay, it's return truth. But how about without just doing this, without declaring induction hypothesis, okay? Of course, he cannot prove that. No successful path, sorry, because N1 is not declared, okay? Yes, it cannot reduce to proof because induction hypothesis he don't know, okay? This term of, if you can use the induction hypothesis, you can easily reduce both time true. But because it's not, he don't know induction hypothesis. This part is induction hypothesis, okay? So you can do this by just pencil and paper, okay? No problems. Okay, so this is a sort of simple one, okay? And the next one is I'll explain. is maybe interesting for you.
Could you please tell us that, do I understand correctly that this associativity of plus can be also proved by induction on the second argument, for example?
I didn't try, but maybe it's a good try. Maybe it can be done. But maybe it's not simple because, maybe second argument it may be difficult because the action is using first argument. Okay. So you can try, just few lines of code. I can do that in 5 minutes, but maybe later I explain that, okay? So of course you are right, such kind of subtlety exists, okay? Because it's nothing assumed, associativity, commutativity is not proved yet, okay? So anything is from scratch. So maybe second argument may be okay, but maybe difficulty. This kind of proof can be a little bit complex. At least first argument is okay. So proof is done, okay? So next thing I want to explain is, more easier one. So it's not trivial. I should say associativity is almost trivial, but of course it's interesting. But the next thing I want to show you is a factorial. 2 factorial is equal, okay? So just try to explain. So pair natural number, okay? This is a pair natural. It is really defined from scratch, okay? Equality over the natural number is defined something like this. But only one equation. If the natural number expressed by the same expression, that natural number is equal. Very, very safe way of, it's not complete definition of equality, but we only need this, okay? Plus is defined like this. Once plus is defined, times is defined, okay? Besides, this is very important, associativity, commutativity is already declared here because like a previous example, associativity can already proved, okay? Similar way, commutativity is also proved. You can look into Wikipedia. Strangely enough, Wikipedia article explain this kind of definition, associativity, commutativity can be proved. Of course, not like this way, just as a mathematics, symbolic puzzle, okay? So we are not getting into this one. This is maybe the first example exercise for my student in this course, okay? So this can be associativity, commutativity also can be done. If plus is defined, times is defined something like this, it's okay? If you have a plus, time is defined something like this, okay? Time is also can be proved associative, commutative in a similar way. It's of course a little bit difficult, okay? But not so super difficult. So that's why I declared associativity. This is a language, very important language, functionality. Associativity, commutativity can be declared. And it's implemented. Because commutativity is really difficult to be used rewriting rules. It's easy to be infinite rewriting. A plus B can rewrite to B plus A and so on and so on. So it's a naive rewriting implementation is impossible. So that's why this kind of attribute is declared, okay? System is taking care of special care. So plus and times is defined, and
so in this code, it is assumed somehow implicitly that this S operation, this success operation.
Yes, of course.
Higher priority.
Yes, high priority. You mean the parsing stuff? Parsing.
Yeah, well, I mean this. Well, in the last equation.
Yeah.
Here, for example.
Yeah. Yes, this is the highest priority because
operations are often of higher priority than binary.
Yeah, well, that is also defined in this language. The user is supposed to define the priority in the parsing, okay? Of course, that is all functionality of this language. But of course, maybe if you are more exact, you can put parentheses, okay? But precedence is declared by users or by default by systems. This kind of thing is possible, okay? Of course, you are right. Usually, unary is more higher precedence than binary. That is an established custom in the expression design. But that is defined, should be defined. somewhere, okay?
And these two words, SOC and POM, it also defined as kind of equations or
this kind of stuff, yeah. This kind of thing is associativity and commutativity can be defined by using equations. Of course, you are right.
Is whether these are language predefined language features.
Yeah, this is a language predefined language features, but also he is right. This kind of property can be defined using equations, but that equation is difficult to be understood as a rewrite rule from left to right. That's why this kind of declaration is prepared in the language, because this language main functionality is reduction from left to right. But associativity, commutativity cannot be simulated completely by rewriting, because if you use the commutativity equation, it's an infinite loop. So
it's kind of a hint.
Yes. Yes. Hint or maybe special way of handling the important property. Associativity, commutativity is defined, handled by this is, I can say, one of the major technical achievement of this kind of language. CafeOBJ and OBJ and mode. AC rewriting, okay. AC rewriting. Associativity, commutativity is difficult to be defined equation and rewrite rules, okay. It's some kind of class rewriting. Associative, commutative equality term is considered to be equality class, equivalence class. That class is translated. It's a one level meta rewriting, okay. So that's a really very important functionality of this. Anyway, in this setting, you can understand this kind of thing is declared, and of course it can be proved in these techniques, okay. Once proved, you can declare this. Once proved.
I mean, that's for the user to prove actually this separate system can.
Yes, before declaring this, the proper way is proving these kind of things. After proof, this kind of declaration should be incorporated into the system. Yes, yes. Before proving, this is, or maybe specifier is confident about this kind of property. Okay. Well, if you write down this property, its specifications. Okay. Without writing that, if you prove this, this is a sort of lemma, or maybe you can't prove from scratch. Okay. And the other thing is this is a distributed law. This can be also proved. Okay. This equation can be also proved in the similar techniques, but we want to do more higher level stuff. So this is also declared. Okay. So this is a plus times, and this distributed law is defined over the natural number. After that, 2 factorial is defined, okay? This is one argument factorial. It's a sort of definition of factorial, okay? Factorial of 0 is 1. Factorial successor n is successor n times factorial n. It's a definition of factorial. This is a 2 argument factorial. It's a sort of, very foundational, typical elementary exercise to accumulating argument, In our old days, recursive call is very costly, and make it more loop, That is, more 2 argument is considered to be more efficient, okay? So anyway, this is a 2 argument factorial. This is a 0 and a second argument is, if the first argument becomes 0, second argument returned. If the first argument successor, this factorial, the second argument should be successor n times a, and the first argument becomes one smaller. You can easily find out some nice relationship here. Okay, this is considered to be more efficient than this in our old ages. Okay. Yes, it's tail recursion or something. Tail recursion. But that kind of optimization is already automatic in many languages. So recently it's not meaningful. But anyway, this is a good exercise, This and this should be equal in some sense. Some nice relationship exists. So it's an exercise for the student, and the nice relationship is something like this. this is a property we want to prove. Factorial ij, factorial 2ij equals j times factorial I. If this identity holds, factorial 2 can be used to compute factorial I, okay? Because, you know, j is a factorial 2i1 is a factorial j, okay? Because j is a 1, okay? So this is the property we want to prove is something like this. And this is a really lucky, beautiful case. Very, very nicely proved by using inductive, our technique of proof squares, okay? So again, we are going to prove this with respect to the induction of first argument, okay? First argument, putting 0 first, and this should be first, okay? This is the base case. Reduction, factorial 0j, j times factorial r, okay? So this returns true, system returns true. So induction hypothesis, because we are going to use the induction with respect to first argument, so pick up I, arbitrary symbolic I, and assume this. It's okay? No secret, okay? Just assuming this. And using this equation and all definition and attribute declaration, and just prove this. Just try to reduce this, okay? If it's returned true, you win. Game is over. Proof is done. So just try to do this, okay? Maybe from here to definition of factorial 2. Of course, it just in case. So everything is load, okay? It's quite fast. This is a simple example. And after that, just opening this one. Opening means looking into necessary ingredient. And first thing is this induction step reductions, okay? Only one reduction, this one. Of course, it's returned true. True means using equations, two sides become equal by rewriting. Of course, it's a lucky case, okay? No, life is not easy like this, but this is a good example, okay? And assuming this hypothesis and doing this one. The second, this is the induction step, okay? Assuming this one. This equation declared. Declare means system knows this, okay? Of course, it's returned true. And it's a like computation. It's a more system cannot count the, you know, it's a less than millisecond, okay? Of course, it's really little computations, so sufficiently fast. So we call it proof score is something like this. This kind of code is called proof score.
Pardon, could you please repeat what is named the proof score?
What's the meaning of proof score?
Yes, what is proof score?
This is a proof score.
The entire...
Yes,
thing.
this is a proof score.
Okay.
And before this is a specification. Okay. Until this point, this is a specification. This is the definition of what we want to define. After the definition, proof score is something, in this case, very simple. So proof score and definition is intermixed here. Okay. After opening this is exactly proof score, induction. More exactly, this reduction and this reduction is a proof score in some sense. Okay. But reduction is, you know, done in some specific context. Context means a name, value combinations, you know. So this reduction is just meaningful in this context. This reduction is just meaningful in this context. This context means after declaring this one. So incorporating such kind of, you know, context, more exactly this reduction, two reduction is a proof score. Okay. So that is, of course, make this definition more exact, we need to do something, but I hope intuitively okay, you know. Context is really important. Context means after declaring this equation, this reduction should be done. Better way is to make module that is only, you know, contains module contains everything, name, association, and necessary equation. It's better to be named as modules. In that module, this reduction is done. That reduction is, set of reduction is a proof score. And if set of reduction design returns all true, you win, okay? If some reduction cannot return true, you should do something more. That is a proof score development, okay? Proof score development. So in this case, it's rather easy. As I said, it's a lucky case. Lucky case. Very easily, very naturally, exactly doing mathematics, okay? But comparing to the mathematical student, maybe high school student has done, in high school student case, these kind of calculations should be done human beings, okay, by some. But if you are clever enough to organize nicely, this kind of reduction is completely done by the machines, okay, in this case. And the interesting point is, what is done by machine is very clear in this case. Just, reducing the both sides and compare. And if you are clever enough to design these kind of things, you can develop nice proof scores. And once proof score is executed, everything is as you expected, proof is done. I can say this is, maybe at this point you can understand this is a complete test cases, okay? Inductions, but complete test cases. I think it's maybe major part is, like this, okay? So maybe I have another example, but this example is, I think, non-trivial and contains almost all functionality I should use, okay? And so, I think it's almost time, so of course there is another issues, but just get into, maybe this kind of thing is a sort of technicalities, okay? So I can explain. Proof square method in CafeOBJ is, as I said, specification is algebraic equation or specification. Specification is all done equations, okay? And as I said, this language is language as it is, it's more powerful, more than equations, rewrite rule, or maybe behavioral equation. It's more sophisticated kind of equation can be declared, but the proof square method is, I should say, equation, ordinary equation until now, because it's logically very transparent, okay? So this kind of, testing proof score is reduction, as I said, but I think it's not needed to explain this part, okay? Development of proof score in CafeOBJ is, this language is, the predecessor of this is OBJ. I participate in this project. It's maybe early 80s and mid 80s, around this community, this techniques is used. But I had a chance to get money from Japanese government and develop this language, successor of OBJ. It's a more advanced, as I said, the behavior stuff and rewriting stuff, around this 1997, 2 or 3 years. And at that moment, we are serious about these techniques to do the verification for any kind of systems, okay? Especially for software systems. And dynamic part is also incorporated. I don't explain that today, okay? And CafeOBJ is a language, as I said, and as I said, it's a language for writing formal models. It's not program language, but executable, as you see, executable. The OBJ, as I said, it's already explained, I participate the OBJ project at the Stanford, it's California, this all time, already 25 years ago, And after that, I continued to develop CafeOBJ, and this book is published around already 10 years ago. And after that, I used this language doing the verification stuff for formal method development. Okay, related work, maybe because St. Petersburg is quite open to the other European countries. So Mode, this is not European, it's an American language. Mode is, the sister language of CafeOBJ. OBJ is a sort of famous, I think the most famous obfuscation language. I participated in that project. After that, Jose Mesega of the University of Illinois, Urbana-Champaign, at that moment he is working for SRI. Maybe it's almost same, years, maybe mode, maybe, yeah, almost same. Maybe cafe is a little bit earlier as an implementation, but this language has I can say at this moment used by many and sort of, the big activity. It's a rewriting logic. It's a little bit different from equation. Extension of equation, you can say, but it's a rewriting logic stuff. And the other related work is CASTLE, is a common algebraic specification language. It's a European activity. It's a European activity. So these three is, I think, the currently, And the other formal method, other formal specification language is, as you know, Vienna development method, VDM and Z and B and event B or this kind. It's also active one. And this school and this school, OBJ, CafeOBJ mode is not competing. This is, early developed. And at this moment, this kind of tool is widely used. This is also used maybe a little bit, as I said. Algebraic stuff is, I think, still has a power, has a potential to improve many parts of formal method. But as I explained several times to you, the piano-like natural number definition or recursive definition and the induction, I think it's very foundational, important, but somebody thinks it's a little bit sophisticated, too sophisticated. Modeling natural number like a piano, I think it's a beautiful achievement, but somebody, it's not fully, get used to or understood by the. And recursive definition is sometimes considered to be a little bit, I don't think it's so, but difficult or sophisticated. So I should say this is a little bit more widely used, and this is still, I think this is the next generation, I hope. Much, nice part, nice property than this kind of things. And I personally committed to this, okay? Executable. Verification based on recursively inductively defined data processes. So everything should be recursively defined. By using recursive definition, you can enjoy the inductive argument and complete case analysis and so on. But I think it's very foundational. Any kind of serious computer science or software technology or language design is no way to escape these kind of things. But this is more, not elementary, but I think it's sometimes, this is more difficult. It's a set theory, okay? Set theory plus this kind of things. Which do you like, okay? And it's some kind of mathematical arguments. Set theory is very powerful, but sometimes semantics can be complex. Okay? You can imagine. Semantics is more clear and transparent here. Anyway, so main feature, I don't think so. Maybe you can look into this slide. Okay, and current status and future issues. Current status, mainly my group in JIST, using these techniques, many examples, the classical mutual exclusion, real-time algorithms, railway signaling, authentication protocol, practical size e-commerce, UML semantics, formal fault-tree analysis. Recently, we are interested in workflow, workflow stuff, because we are concentrate on upstream of the stuff, okay. And I can say, 1, 2, 3, formal method or in this language, writing down formal specification improve your understanding. Just writing down specification is really important, okay, without doing anything. But of course, next step is doing some kind of prototyping, simulations, animations, okay. And final is PRU-score, you know. I personally think writing PRU-score and check the property of a specification is the main purpose is making quality of your formal specification rather higher, you know. Verifying something is of course important, but more than that, by verifying something, you can find many problems in your specifications, okay? So verifying specification is best way to get high quality specifications, okay? Even if you cannot prove the property you want, you know, because to verify every necessary property is just impossible. Because what kind of property you are interested in is not clear from the scratch, okay? Just after doing something, you can gradually aware the important property of your problem, your specifications. So I personally think the major importance of writing PRU-score is making a quality of the specification rather reliable. Okay. So 1, 2, 3, just developing formal specification, doing a little bit rapid prototyping. It's like a programming, you know, just after developing a pair natural number, just 2 plus 3, 5 plus 9, okay, such kind of things. And after declaring distributed rows, you can put in some data as testing, okay? But this is more sophisticated. PRU-score writing is more sophisticated. You can. Of course, this is recommended, but it's, I should say this is sometimes not simple, okay? It requires some kind of abstraction and mathematical, you know, thinking. It's required, and I think it's needed to do that, okay? But this is a final level, okay? So maybe this is an interesting argument. What I want to say in these 3 slides is I think this is a minimal, you know, simplest kind of formal method. If you want to do some serious, some meaningful verification for any kind of things, I think this is a sort of minimum requirement. Minimum requirement means algebraic modeling, you know, maybe it's somebody said it's a sophisticated, you know. Explaining natural number like a piano is too sophisticated, but I don't think so. It's maybe the simplest way to define natural number, okay? Without avoiding such kind of recursive or maybe axiomatic way, what's the best way to explain the natural number to the first persons, you know, for example, elementary student or your children or high school student? Of course, you can explain in many ways, you know, but sometimes quite complex, you know. So algebraic modeling, it's some kind of object-oriented modeling, you know, and the other one is equational logic. As I said, equational logic is the most foundational in some sense, but most foundational at the same time most powerful, very powerful logic, okay? And rewriting and the proportional calculus, this is. Other one is for doing PRU-scores, as I explained, induction is needed. Induction is understood. We use today is just induction over the natural number. But, of course, writing serious specification, you are supposed to do induction over term structure. As you know well, induction can be used in many ways, you know. So this is, of course, sort of sophisticated, but I think this is very important and very foundational. So writing down PRU-score using induction and case analysis, I didn't explain this, but case analysis also should be done. You know, case analysis means whether or not some predicate is true or false. Okay, you can divide your word true case and false case, writing PRU-scores. Okay, it's a usual thing in software, any kind, or testing or something. Okay, so such kind of case analysis also done. So induction plus case analysis. And sometimes you need some lemmas, you know. Do you remember that I declare some factorial 2 and factorial 1 is this equation. You think it's quite natural, okay? But Usually that kind of relation is supposed to be found, provided by the users, okay? No way to deny such kind of things. It's some kind of invariant assertion or something, okay? And of course, it's sometimes it's difficult, to find out nice relationship between, we call it lemmas, okay? Lemma finding is done. So induction, case analysis, lemma, it's a three basic techniques. Any of them is really foundational, but doing this kind of argument requires some skill. I should say it's not simple. I cannot say it's simple. But of course, I at the same time I can say this is a minimum, Without using any other techniques, this kind of complexity exists anywhere. But I should say the complexity of this technique is really low comparing to other one. That's what I want to say. Other thing is traceability. As I said, the user is supposed to define their problem, their property using equations, okay? That equation is exactly used by reducers, reduction engine, in this language processor, okay? No transformation, no other stuff. Usually the expression user is giving to the system translate that to other things and do something. That is common. But in this system, equation is supposed to be action. Equation is really specification, So most, yes, it's action defined by users. User is responsible to write down that equation. That equation is exactly used by reductions. It's a traceability. So if something wrong happened, I should say it's rather easy to find out why that kind of strange things, what's that kind of thing happened. You can identify which equation is the cause. Of course, we have tracers and so on, steppers, seeing the simulations. This traceability is not common in other kind of tools, okay? This is quite specific to these techniques. And I don't need to say anything. It's in equational reasoning by reduction. Equational reasoning by reduction, We only use reduction. It's very simple paradigm. I think it's quite powerful, especially in computer science. This system is CafeOBJ is just doing the reduction, which is honest equational reasoning. Partial, okay? Of course, partial reasoning, of course. If you have a power of full equational reasoning, you can solve everything, okay? You can solve, but it's impossible. So future issue is, of course, environment of this kind of stuff and more serious example. We are now trying to write down more serious formal specification using this language. And for example, now I have some interesting, I was supported by Japanese government and now trying to develop a formal specification for the automotive software. Automotive means, the onboard computer. Small, that is really important. If that computer is working wrong, you lost your life, okay? So it's really socially important problem. Other thing is, to develop some kind of middleware protocol, cloud protocol and so on. Anyway, it's a high level standard-like stuff, before coding. Because coding area is, of course, it's very active and very important, but it's already sort of large-scale research activities. If you need to hire many people, okay? You need to make a big team and doing the code analysis systematically, like a Microsoft, okay? I personally think it's not a good idea to compete with such kind of stuffs, And of course, at the same time, code verification requires many kind of program language stuff and so on. And our interest is more a requirement to a design side, So we are concentrated on that. Okay, so as I said, e-commerce and automotive. This is automotive OZEC VDF AutoZa. This is exactly, we are just finished the first version of this. It's a 100-page. Of course, whole stuff is 1,000 page, but what we are doing is task scheduler, process scheduler of this part. Okay, so if you're interested in looking at that, this is a GIST. Okay, LDL is our group's name, Language Design Laboratory and CafeOBJ. Or you can go to CafeOBJ. I'm quite sure first hit is this page. Okay.
The first hit will be Wikipedia page.
Wiki page? Oh, really? Yes.
What are the main advantages of CafeOBJ approach of scores with respect to model checking?
Model checking. Model checking is, as I said, it's a big achievement, okay? But model checking, what you can do with model checking is just finding counterexample, okay? If you cannot find the counterexample, the information you got is, for this kind of finite case, there is no counterexample. So your system seems to be okay, okay? That's all. This case is complete proof. For example, factorial, or today's example, is true for all natural number, no limitations.
Right, but we checked one assertion about this whole specification. You cannot say at each point, it seems to me, that the specification is complete and correct.
Yeah.
We only check it iteration by iteration, part by part. Making assertions proves scores.
Yeah, proof score is supposed to be verification, mathematical verification. So the result is hold for any natural number, okay?
It's all about symbolic calculation, right?
Yes, symbolic operations.
That's
And, okay, even in symbolic model checking, of course there is an argument, abstraction plus model checking is a proof, okay? But in that case, you need to find out abstraction, nice abstraction. And usually model checking is only can teach you with respect to finite area, there is no counterexample. That's all information you can get from the model checking. This technique is completely different from that. This technique, if you use properly, exactly today's example, you can prove infinite statement because it's mathematical argument, okay? You can prove infinite argument.
But there might be several infinite statements about the specification. We can omit some statements. And still have a proof score which is true. But our specification can't be complete. We left something out.
Yeah, but specification of natural number is, of course, it's a complete specification of natural number.
Because it's a tiny specification. For example, but if we have a large specification with a lot of equations, and we need to formulate a lot of proof scores.
Sure.
We can omit some proof scores and still have okay.
Of course, you are right. The proof score, the size of the proof score has become large, But I think it's even if you use a model checking, the same thing happened, okay? If the problem is complex, even if you use a model checking, your specification should be large, okay? And even if you use a model checking, what you get is exactly what I said, okay? And so it's a scale problem is both is a scale problem, okay? And model checking is nice part is, of course, it's automatic, okay? Automatic. So you don't need to write down the proof score by yourself, some cases. But result is limited. Result is just give you no counterexample. And if you are serious about verify some property which should hold, of course, infinity is not needed by practice. But no upper bound exists is quite common, If you want to prove something, for example, mutual exclusion, okay, it's really nonsense to assume up to 100 processes or up to 1,000 agents, this statement can be proved. It's okay, but it's sometimes really nonsense to prove such kind. And I should say, to prove such kind of statement is more and more difficult than using that, okay? Other one is, and I think that's kind of statement is sometimes very dangerous, whether or not this is really true or not, okay. And of course, model checking is, of course, successful and really nice techniques, but you should understand the difference of model checking and this kind of infinite, finite or interactive verifications. We are serious about this kind of interactive verification because we are interested in upstreams, okay? In that case, we need to identify the important property which is hold for any kind of systems. Yeah, again, the model checking is powerful because it's automatic. It can be used properly. It's very powerful and a big success. But the community of model checking is also aware of the same issues and try to do other things, the abstraction and so on, so on. Okay. So I hope I reply your answers. Okay.
Can you give a few words in comparison with other systems, the French system Koch?
Yeah.
With this?
Yeah. Yes, that is interesting. Koch, Hall, PBS, French, Britain, and America. All that is a higher order logic. Okay, higher order logic. And it's a nice system. I can say this is one of the most important achievements in computer science, especially Koch or Hall. And many activities and many investment is, or much investment is done. But it's different. I can say it's completely different approaches. This is algebraic, and that is it's just equation logic, no higher order. And our hope, this is, as I said several times, very transparent, simple, light-weighted logic. Okay, there is a powerful but very higher order logics. And I think this kind of the logic is better to be used in more lightly, more casually in the software engineers. That's our hope. Okay, so it's a different approach, different logic.
And you have such examples of successful application.
There was a slide that would listed the applications.
Yeah, application is of course we are in the middle. I should say it's still research stage. But for example, the important problem in the software engineer by writing down standard specifications, okay, and more. And our idea is, Plus score is better to be put together with the formal specifications. High-level document is a formal specification plus Plus scores, and that is really reliable document for defining the very, important software systems or standard or protocols. Okay. Of course, similar thing is attacked by other approaches. What we want to see is more, the usable. Usable means software-oriented specification. For example, the language, this CafeOBJ is, from scratch, designed to write down specification of software systems, But the PBS, Hall and something is originally defined to write down the mathematics, okay? Of course, they are extended, many things, four-color problem and so on, so on. But it's, for example, this language has a quite powerful module systems, okay? And I think that kind of thing is some difference. And maybe, of course, ML is another module system, ML is a Koch stuff. And some focus is different. They are more serious about the mathematical mechanization. But I should say, I am not saying this is much better than that. I should admit their achievement is really nice and one of the best, most profound result in computer science. But still should be be done something up because software field is more widely. It's more than such kind of things. Okay, so many attempts should be done, and I hope this kind of techniques can give some another applications. Okay.
Other established approaches to incorporate the temporal logic into this system.
Temporal logic, it's really good questions. Temporal logic is widely used in combination with model checking.
Yes.
Okay. So today I don't speak to this how to model dynamic system in this language. But at this moment, we didn't incorporate temporal logic, But similarly, what we want to do at this moment is just proving the safety problem. Safety means the property which holds for all state, reachable state. And temporal stuff is the sister language mode, Mode is a very similar language. That is a more, interested in model checking technique. They have LTL model checkers, temporal logic stuff. And our current, hope is combining this kind of inductive techniques to the model checking techniques. And if you really want to use a LTL or CTL stuff, that kind of combination can be done using two languages. Okay. My group now don't incorporate LTL because we are more serious about the other side of stuff. Temporal stuff is sometimes difficult. Yeah, I know. Yeah, it's an interesting area. I hope I can give you some, very concrete stuff, example. Of course, it's a tiny example, but so sorry, time is over. Okay. So I'm okay. If you have any question, I'm happy to reply. But it's maybe time to finish or something. Okay. So thank you very much.